Yeah, ladies and gentlemen, if you'd listened to the introduction there, I've never done any work in estuaries, so this is becoming quite a new area of research for me, so bear with me. In 2015, the Department of Water Affairs did a reserve determination, in the Mlalazi, and realized that the hydrology and hydrodynamics and mouth dynamics of the system was not understood, and it was creating a problem in terms of reserve determination. So we became involved in looking at the Mlalazi estuary. One of the things we discovered early on is that this thing is controlled by both the fluvial runoff from the catchment and as well as the marine interaction with the estuary. And what we wanted to understand was how the fluvial systems, the big runoff events, propagate through the system and how they interact with it, and at the same time the opposing tidal system moving up the estuary. For those that some of you may know this, but the Mlalazi estuary is just south of Richards Bay. It's on the town of Mlalazi there. It is has a catchment area of about 400 square kilometers, and it has 3 tributaries there. Something's happened to my slides here. I don't know what's happened, but anyway. So that is the catchment contributing to the estuary. When we did this, we got quite a lot of information on rainfall. We have some sites there with runoff data. But what we were really lacking a lot was some idea of the symmetry of the estuary and the floodplain. And I was very fortunate that my colleague, Ricky Taylor, and Bathos from Isabella Wildlife surveyed the whole estuary. And that was in 2016, and then 17, Water Affairs came in and did a more comprehensive one down the southern end of the estuary. This is the estuary here. All right, and Water Affairs surveyed that accurately, and Ricky and Santos did the whole estuary for us. So we ended up with a good bathymetry of the estuary. The floodplain, we had no information, so we had to go out there and look up spot heights from SRTM and surveying and mapping, and then we did some extensive field work in there with honor students to plot what is the floodplain there of the estuary. That allowed us to come up with the hypermetric curves for these things. The one on the left is the stage area volume relationship for the floodplain. The one on the right is the same one for the actual estuary. So this allowed us to start looking at the propagation of these systems through the estuary. My colleague, Joshua Rasafuri, then modeled the catchment to try and provide us with a range of storm events so that we could look at how these things propagated through the system, because we had no data. There are a couple of gauging sites on the catchment. This is the discharge into the estuary. There were no gauging sites in the main part of it, so Joshua set up the HMS, Distributed Hydrological Model, and using calibrated flow records for a short period of time, and selected storm events, because we had a whole range of storm events there in the 60-year period of rainfall that covered up to over a 100-year event. The 87 flood was classified in some cases. Some people thought it was about 150-year flood. Joshua calibrated the model against 30 years of runoff data and storms, and then validated it against an independent set of runoff and storm events. Then he provided for us a whole 68-year series of runoff and sediment production from the catchment. The nice thing about this is it gives us a full range of storm events, right from average conditions up to 1 in a 150-year flood. Now, to try and understand how these floods affect the estuary, we have an example from a recent survey there where we have a hydrograph. This was a storm event of 150 millimeters that occurred over 48 hours. Actually, it was close to 200. This is the hydrograph in the upper sections of the estuary, the confluence of the two rivers. This is the hydrograph at the mouth. And what we wanted to do was understand a little bit more about the attenuation of these flood events as they move through the estuary, and look to see what sort of level of lag there was between the peak flows in the top of the estuary and the bottom of the estuary. So what my colleague Lesiba Mabaso did, he got some water level measurements, historical water level measurements. This is a photograph of the 87 flood. This is the old N2, which is now the 102. This was the start of the new N2 up in Mtunzini there. This is the site up here from these old historical records, so we knew what sort of level the water level was there, and they had a few other survey points down there for a couple of other floods. So we did have some measurements of water level to be able to validate our model. Now, Lesiba set up the HEC-RAS hydrodynamic model, calibrated against these floods, and set up a means of mapping the extent of these floods. This is the transects that he used in setting up the model. It's every 40, 50 meters he had these, and he simulated the flow through the different transects. Having calibrated it, he then is able to give us the water level through the catchment. This is the top end of the catchment here, about 11 kilometers. He was working from 11 kilometers up from the mouth, predicting the water level at different points in the catchment. These are measured historical values. We were a little bit out here, but we're getting quite close down there. Unfortunately, we had no historical data for the mouth, but he's able to give us this now. This is for a 100-year event, which is equivalent to the 87 floods, and he can provide that for any level or any storm event that we want. With the same model, he's able to now provide us with the distribution of a flood event. The one there is the 20-year event. The light shading, or the blue shading here, is the depth of water over the floodplain. This is equivalent of that as a 50-year event, so it can give us the depth of flow and the extent of flooding. And the equivalent down here is the velocity, so we are able now to map areas of deposition and areas of scour inside the actual estuary itself. So we're able to predict those now for any size event that we need to look at. Now that's from the fluvial side, the storm runoff. What we wanted to know now was looking at the reverse flow, the marine tidal interaction. We're fortunate that we've got flow data, or we've got tidal data here from Richards Bay. The time of the Richards Bay high tide and ours here is only a matter of minutes apart. Water affairs have a logger here right next to the mouth. By the way, this is the bathymetry that Ricky and Santos provided. So it's water affairs logger there. It it ran from 2014 to 2015, and then it was flooded. We put a substitute logger in there for 2015 and 16. We also put loggers in the back channels and salt marshes and that in this section of the estuary. These in Velo Wildlife have a logger here, and we put another one at the confluence of the river, the top of the estuary up there. And these are just examples of the water level traces that I've taken from those particular loggers. Now, using this data, I can't go into all of these, so I'm only going to highlight one or two points that have come out from this. This is the marine tide that propagates through the mouth and into the estuary, and this is the resulting hydrograph or tidal pattern for that particular marine tide inside the estuary. You can see here, going through the mouth, we have an attenuation of those peaks, certainly the high tide. There is a lag between that high tide and that high tide there of about 4 hours. But the thing I really want you to focus on here now is these peaks, high tide, corresponds fairly closely with the marine high tide. What is important here, we find that with the onset of spring tides, we're getting water storage in the catchment and the estuary, and it's being released as we go from spring to neap tides. So we are getting the storage that's carrying over the spring neap tides. The other one that I found very interesting is if we look at the tides in the estuary, and this is an example of the estuary tide at the mouth. The flood tide has a duration of about 4 hours. The ebb tide has a duration of about 8 hours. Now, if we assume that there's no change in the mouth conditions over a diurnal tide, 12 hours, then that means the velocity over the flood tide is double the velocity over the ebb tide. And what this is doing is the flood tide is bringing in larger sediments that the ebb tide can't take out again. So we're getting an accumulation of larger sediments in the mouth. By the way, this is just all them plotted together and just the average ebb tide and flood tide on that. This is an example of what actually happens when we see the mouth closing. We're getting sediment deposition until finally the mouth closes. This is the water level trace in the estuary. It was breached here, but it slowly built up here. What I want to harp on is what we're seeing here now. This is a section of that trace. This here is the tidal action, high tide, low tide. We get the storage over spring tides and the release of the storage. But the minimum low tides here is where we're getting that rise in the estuary mouth elevation to the point where there is no tidal interaction here. So this is something that happens on a regular basis. At this particular point, we don't know why, but there was a sudden increase here. There's no tidal interaction. As the mouth built up, it could have been wind action or storm action. But clearly we have a regular increase in the base elevation of the mouth according to this differential between the ebb and flood tide. So basically, the fluvial systems are random storm events that disrupt the cyclic system. They do scour out the mouth, the sediments to some extent. From the marine side, we have water storage over spring neap tides. And then the irregular variation in the ebb tides create this differential in the sediment production at the mouth, and this is what causes a slow, progressive increase in the mouth and leads to mouth closure. Thank you.